So, hello everyone. There were some problems with my microphone again, so I will start now. It shouldn't be very important, right? Oh, let's switch to English. Well, okay, so in problem A, we are given permutation and we should check if it is a cyclic shift of sorted permutation or reversed sorted permutation. So this is an easy implementation problem. The limitations are very small, so we can, for example, check if every cyclic shift is sorted permutation or reversed sorted permutation in linear time, and the total complexity will be quadratic, but we can do it in linear time also. For that, we can say that there can be only one cyclic shift which is sorted permutation, and this cyclic shift have the first element equal to 1, so we can find what is the position of 1 and do corresponding cyclic shift, and then check if the permutation is sorted. And for reversed sorted permutation, we can just reverse the permutation we had before and do the same thing. So let's write the solution in quadratic time first. This is just a code to do multiple tests. So we will have function check that checks if our current permutation is just sorted permutation. That's pretty easy. Each element should be equal to e plus 1, and if it's not true, then our permutation is not sorted, otherwise it is. And now we have to check n cyclic shifts and the reverses of them. To do it, we can do something like this. Well, it will be better if our function solve return bool, then we shouldn't write these returns many times. We just say return true and everything's fine. C++ has built-in functions for reverse the array. It takes pointer to the beginning and pointer after the end of the array. And it has a built-in function for cyclic shifts. It takes 3 pointers to the beginning of the array, to the end of the array as the third parameter, and as a second parameter, like the pointer to the element which will be first after our cyclic shift. And since our function solve is now return bool, we should print the answer here. So it looks like our solution is good. We can submit. And now we can write faster solution. We still need to read our array. We still will use our function check, but now what we want is to find the element equal to 1 and check only the cyclic shift that has this one on the first position. So let's find the position. We know that there is one element equal to 1 in our array, and while we are not found it, let's check the next one. So now we just do our cyclic shift, which again takes the pointer to the beginning, pointer to the end, and pointer to the element which we want to be on first place, and this is exactly our one. We want it to be on the first place. So this is our cyclic shift, and if it is sorted, then we return true. But we also have to check if maybe the reverse of our permutation is fine. We can see that the cyclic shift of reversed permutation is the reverse of some cyclic shift. So it doesn't matter that we already make some cyclic shift of our first permutation. We can just reverse it now, and now it is the same as do reverse first and then do some cyclic shift. Well, it is easy to see that if we do cyclic shift to x positions to the right and then reverse, it is the same as do reverse first and then cyclic shift to x positions to the left. Since all the cyclic shifts are identical for us, so it doesn't matter really. And we can do the same thing as before. And this should work too, and now the solution works in linear time. Oh no. Oh, it should be while our element is not 1, we do this. Yeah, now it works. Why it works in linear time? Let's see. This while is linear. This both functions rotate and reverse work in linear time. Obviously, like it is easy to implement them in linear time. So it's safe to assume that they implemented in linear time, but well, actually you should check like CP reference or something. But yeah, I know that both these functions work in linear time, so you can trust me on this. And function check is also working in linear time, obviously. So first our check works in linear time, then we do reverse in linear time, and then we do this check again. So everything works in linear time, and we can submit it again. Well, okay. So problem B is about creating rectangles from given sticks. We have 4 n sticks, and we want to create exactly n rectangles, so every stick should be used. To create a rectangle, we should take 4 different sticks. They should form 2 pairs. In each pair, sticks should be of equal length, and the area of rectangle is well, obviously product of the sides, so it's product of lengths of well, first group, first pair and second pair. And we want to check if it is possible to create exactly n rectangles which all have equal areas. Well, obviously, first of all, we should divide all sticks to 2n pairs of equal lengths. If we can do this, we're screwed. And obviously, we cannot create 4 n rectangles at all, not to mention some areas. So now we have 2n numbers, and we should pair them such that products in pairs are all equal. Then it is kind of obvious that we should match the smallest number with the biggest, the second smallest with the second biggest, and so on. It is the only way to guarantee that the area can be equal. Like, otherwise, we will have 2 different pairs such that first number in first pair is smaller than first number in second pair, and second number in first pair is smaller than second number in second pair, so the products cannot be equal, like there is no way. So we can sort all the numbers we are given, check if two consecutive numbers are equal, like pairs of consecutive numbers, like first and second, third and fourth, and so on, are equal, and the products of numbers, the smallest and the biggest, the second smallest and the second biggest, and so on, are all equal also. If all of that is true, then we win, otherwise we lose. It also has multiple tests, and also the answer is yes, no, so the main will be the same. It's important. It says that n is up to 100, but we actually read 4 n numbers, so the size of our array should be up to 400. Numbers are up to 10,000. The product is up to 10 to the 8th, which is fine for int, so we don't have to use long longs. Now we sort all the numbers. Check if consecutive pairs are the same. If they are not, then the answer is no. I said that we should compress pairs of equal numbers, but we can not do it, and everything will be fine because the pairs of consecutive numbers are equal. So we just checking all pairs 2 times, well actually 4 times, because like we are checking it. For example, the first pair we check when I is equal to 0, then 1, then n minus 2, then n minus 1. But the limitations are small, and actually the longest part is the sorting, which works in n log n time. This is linear, even if multiplied by 4 for some reason, but that doesn't matter. Problem setters like samples with answers yes, yes, no, yes, yes. You can see that I'm not checking the verdict. You can think that because I'm pretty sure that it will be accepted, but that's not really true. Well, I am pretty sure, but that's not the point. The point is checking, like waiting for the verdict is stupid, and you should never do this. If you have something better to do, you should do it. For example, you can read next problem, even if, like, obviously, if you have 5 minutes before the end of the contest, then you can wait for the verdict, but actually it will be better if you assume that it is wrong answer or time limit or something, and try to find bugs in your code before you know the verdict, because like if the verdict is accepted, you will do just nothing for 5 minutes, and well, that's stupid. And if the verdict is not accepted, you will try to find bugs in your code. So you can start now while wait. If you have much time left and you have other problems you didn't read before, well, read the problems. Well, okay. This sentence is exactly the problem. We have to find the number of common divisors of all the elements, and well, it is known that all the common divisors are the divisors of greatest common divisor of all the elements, and so we should find the GCD of all the elements in the array, and then calculate the number of its divisors. So there are like two separate problems. Both are fairly easy and standard. To calculate GCD, we just will calculate GCD of we say that the result is like first number, and then calculate GCD with all the rest numbers. Then we will get the GCD of all the elements, and afterwards we will calculate the number of divisors in square root time, just like we will find all the divisors basically. Let's do it. There is built-in function GCD, but I'm not used to using it, so I write my own GCD all the time. It's kind of stupid, but we don't actually have to store our numbers. This file like read n numbers and do something. I said before that we should set that answer is the first element and then calculate GCD with all others, but actually it's even more right to say that answer before all of this is 0, because like 0 is a neutral element according to GCD. Like 0 is divided by everything. So GCD of 0 and x is always x. So GCD of 0, 0 is 0. That's like kind of an agreement, but it makes sense. And our GCD works exactly like this. If we like, if this y is 0, then we will return x. So now G is GCD. The number of divisors can be big, like for numbers up to 10 to the 9s, it's less than 2000, and well, I guess it will be less than 10,000 for 10 to the 12th. Well, we can for sure say that we will find all the divisors in square root time, so we are good. So we're just trying all the divisors which are less than square root of well, less than or equal to square root of g. If it's not a divisor, then do nothing. Otherwise, we find two divisors, x and g divided by x, but they can coincide, and we are checking for it here. Like, if they're not coincide, we should add one more. Well, that's not great, but I'll take. What is the complexity? But we all know, or we all should know, that GCD works in logarithmic time. So this is n multiplied by logarithm c, and this is square root of c. But actually, like, this is square root of c. No questions here. But this works not in time and multiplied by logarithm of c. It is actually n plus logarithm of c. To prove that, we should like understand how the GCD function, which is Euclidean algorithm, works. Well, why it works in logarithmic time? That's because like every two, I think, or maybe three, like constant number of operations, our numbers will be divided by 2 at least. So there can be no more than logarithmic number of steps. But like, if we take these 2 or 3 steps to divide the result by 2, then it will always be divided by 2. Like, we are calculating GCD of a set of numbers, and we always call in GCD function with the result of previous call and some new number. So this total result will gradually decrease. So obviously there is a first call which will always always happen. So we are spending at least n operations. But all consecutive calls, like not all of them, but let's say starting from third one, every 3 calls divide the result by 2, and there can be no more than log c of these operations. So there is first call, which happens n times, and maybe there is always the second call, but every 3 calls after that, we are dividing the result by 2, and actual complexity is n plus log c. So we can submit that. Oh, base, okay. So okay, in problem D, we have some big string S and smaller string T, which is guaranteed to be a subsequence of string S, and we want to remove some contiguous substring from S such that T is still a subsequence. There are two versions. In first, lengths are up to English is hard, up to 200, and in the second, lengths are big and we should solve in linear or something close to linear time. Well, in first one, we can do any crazy thing we want. Well, how to check if a string is a subsequence? Well, the answer is we can do it greedy. Let's find we should find occurrences for all characters in order. Let's find the occurrence for first character. It's easy to see that we should take the first occurrence because it's always good. Like if there is some answer in which we take not first occurrence, we can change it to first and it still be a subsequence. So we can take first, and like from here we have the same problem for the rest of the string, and everything that are on the right from the occurrence we take. So we can actually check in linear time. So the first problem can be solved in cubic time just by trying all the substrings of which there are cubic amount, and on what remains we just try to find the T as a subsequence of what remains. So let's do this. So we just read our strings, check all the substrings of S, we deleted it. I guess that should be right. And if there is a subsequence of what remains, we just relax the answer. So, okay. We'll just go for all characters of string T. actually don't need. Do this and try to find the closest occurrence to the right from the position like which we can use still. While we didn't found do plus plus plus, if we reached the end of the string, then t is not a subsequence of s. Otherwise, we found an occurrence, and we should do plus 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 once more because we already used this symbol. Otherwise, we found all the symbols of t and order, and therefore t is a subsequence of s. We don't use it, right? We don't. So this works in cubic time, which is fine for problem D1, but not very good for problem D2. Now we should think for a bit. Like for problem D1 we don't have to, but for D2, well, the idea is that like I have some thing where I can do some painting. I'm not familiar with this, but okay. So we have our string s, and we will erase some part of it. From here to here. After that, we will try to find t as a subsequence. What we will do? We will go through characters of t and find like closest occurrence of each character. Like, let's not even think about it in this way. Just after the deletion, t must be a subsequence still. So there is some occurrences of characters in t, and they form whole string t. We can't use this part. So what should we do? I already said that to find a subsequence we can go just from left to right greedily and take every character if it is good for us. So we can do the same backwards from the end of s and the end of t. Moreover, we can do it in the same time. What I mean by that is that we can start going from left of s and t, go to some place, and then start going from the end of s and t, and also go to some place. What we have to do, like we will find some prefix of t here, and this will be the leftmost possible position where we can find this prefix. And like the same, we will find some suffix of t here on the right part, and this will be the rightmost position where we can find this suffix. So we have our string t. It will be divided to prefix and suffix, and prefix is here and suffix is here. So what if we will fix where this division between prefix and suffix is? So if we fix this, what we want? We want that prefix will be found in the left part of our string s, and its end will be as much to the left as possible. And the same thing goes for suffix, but now we want it end as right as possible. If we find this, then what is the substring we can delete? Well, it's easy. We can delete, like we should left all that, like this symbol and everything to the left. We should save this symbol and everything to the right. Everything between them we can delete. And if this is the border we go with, then this is the optimal substring, because like this is the leftmost. We have to save this part, and we also have to save this part. Everything between them we can delete, and we will do it. So for fixed border, we just have to find this position and this position, and relax answer with everything between them. Now we obviously get a solution in quadratic time. Just try all the borders, the linear number of them, and for every border just find the, like, run the greedy algorithm finding substring from the left for prefix and from the right for suffix, and update the answer. But actually we can do all of this in the same time, in linear time. For all prefixes, like how our greedy algorithm works, we take first symbol and find its leftmost occurrences. Then we take second symbol and find leftmost occurrences to the right of the previous, and so on. Like if we are solving, like we are doing our greedy for whole string, we also have solved this greedy for all prefixes, and we did it in linear time. Then we do the same thing for all suffixes, and then just check all the borders, but now in constant time, because we have pre-calculated all the values. Let's do this. We don't need all of that. We can reuse it, but let's not do that. So solving for all prefixes. We should remember that both prefix and suffix can be empty. Well, not in the same time, but prefix can be empty and suffix can be empty. So we should do fair job of remembering correct values for these cases in accordance with all other values we'll calculate. For example, now I think that we will remember like the position where the last letter occurs. If the prefix of length 0, then this position is -1. How absurd is this? But well, actually it's true, because we have to left 0 elements. Like we can delete 0's element. So the last element we should save is on position 1 before that, so it's -1. Well, I should write something like this, but it is guaranteed that t is a substring, so we are good. Like the same thing. The last, if the suffix has 0 length, then we shouldn't save anything. We can use symbol on position n-1, so the last symbol we deleted is on position n. Oh, and it's in array B. I used I+1 here and I here. Like I just want such that for the same border, the indices are the same. Obviously, in one array, I should move it. Like I can't remember like for the last symbol for the prefix and for the last symbol for the suffix, because the symbols are not the same. I will move for the prefix because otherwise here should be -1 and that is not convenient. Remember to include both endpoints, 0 here and m here. Like if e equals to m, it means that all the t are on the prefix and suffix is empty. And now we should write something like this, but actually -1. Like this is the last symbol on the last position on prefix we save. This is the first position on suffix we save. So to get the length between them, the number of characters between them, we should subtract 1 here. Oh yeah, I can write stupid cube. That's cool. Well, okay, we have some array of numbers. We can change them by no more than 1. So we can do -1, +1, or don't do anything. And we want to do the separation such that the number of different numbers is as large as possible. Well, this looks very easy. Don't know. Like, it seems for me that we should sort these numbers and there is no reason to like ruin this sorted order, to do something such that numbers become unsorted in this order, because we can change our operations such that like the multiset of numbers will remain the same, but it will be in right order, and then obviously we should just go from left to right in sorted order, and try to make current number as small as possible, but in such a way that it is unique, if that is possible. So I don't know. For me, this problem is much easier than D2. I don't know what to say else about this problem. We cannot go less than 1, so I guess that's all. Like, oh, that's not true. Well, okay. Let's not do this. Let's do this way. Okay, I'm trying to find the smallest number I can use and I can become, and it is still not used by anyone before me. If I can find this number, I became, and that's all. I don't understand. Well, okay. In problem F, we have some projects we can complete. We can choose order in which we complete all the projects. And for each project, like we have some rating. For each project, we know the minimal rating we should have to be able to complete this project. And after completing this project, our rating will change by some value, which is not very big. Like, it looks like our rating is always between 0 and 60,000. Our rating cannot can become negative, and in first subproblem we just have to check if we can complete all of the projects in some order, and in second subproblem we should find the largest largest number of projects we can complete in some order. So okay, there are some good projects for us and some bad projects. Good projects are obviously the projects that increase our rating. And it is easy to see that if we can complete some good project, we always should do it. And we can do it right now. There is no need to wait for something. Like, it is always good for us to complete good projects. It is one project completed and it increases our rating, which is good for being able to complete other projects, and it is good for not going to negative ratings. So at first we should just greedily complete every good project we can, and like, after completing some good project, we should check if there are more good projects now available. Since the number of projects is very small, we can do it in quadratic time, for example. Like, every time, just go through all the projects, check if the project is not yet completed, is a good project, and we can complete it now. If all of above is true, then we can complete it now, and it's good. So after that, after we do it and there are no more uncompleted good projects which we can complete now, then obviously after that our rating will decrease. Well, it will not increase anyhow, because like, now we can complete only bad projects which decrease our rating, and there cannot there won't be any good projects available for us because our rating is decreasing, and we cannot complete we were at our best before doing all these bad projects, and there won't be any new projects we can complete. So everything will be divided in two parts. In the first part, we are greedily completing good projects if we can. in second part, there will be no more good projects. We're completing only bad projects, and we're just trying to, like, in first subproblem complete all of them, in second subproblem complete as much as we can before going to negative. So I don't really see how the second problem is much harder. Like, the only difference that you still have to know have to come up with all the greedy ideas, and I didn't mention all of them yet. But in the second subproblem, we should do some knapsack-like DP, and in first, greedy is enough, but in this problem, greedy ideas are harder than knapsack. It's just, well, if you don't know knapsack, you couldn't accept the second problem, but if you do know, first and second are kind of the same. So, what should we do in the second part? Like, first part is easy. We just in square time. It can be done faster, but we don't have to. In the second part, we have some bad projects, and we have to choose, like, what projects we will do, and in what order. Well, and I want to say that the order is greedy, but not by the change in rating, but greedy by the rating, minimal rating we need to complete this project. Why is that? Like, let's fix the set of bad projects we will do, and now I say that we can reorder then. Like, first do like the hardest in some way projects, like the projects that that need greater minimal rating. Well, the idea is that in each step we should choose the project with the greatest minimal rating, because if we will leave it for later, then it will become harder and harder for us to do this project. So if we can leave it for later, we shouldn't do this. Oh, that can be not true if if like this project is like giving us too much bad delta, but I guess it will be true if we add A and B for each project. Like, okay, delete all of this. How to do that? Okay, I don't know. No, that's not what I meant. So okay, like in all this, like not in all, but in most problems where we should like greedily choose some order. Well, you obviously don't know if we should do this greedily, but okay. On problems where we should choose some order, we can prove some greedy ideas like sorting by some parameter using exchange argument. The idea is the following: like suppose we have objects sorted by like we have some correct order. And we want to prove that actually it is okay to do greedy. So to prove this, we can try to think like that. Suppose there is some order, and we want to prove that some greedy is also fine. Then we can do some changes in this order, and the easiest change we can do is to swap two adjacent elements and prove that after the swap order is still fine, and like if this swap is done according to our greedy. For example, I say that like correct greedy is to sort by a plus b. I say that b is all negative or not positive, but it's not important. Sort by a plus b in non-increasing order. So at first we should do the projects with greater value of this, and at the last with smaller. So what does mean by swapping if like the order is, so I want to get some correct order, and then by doing swaps get to my order, which is sorted. To do this, I will find two adjacent elements which are not sorted by my rule and swap them. If all such swaps are fine, and so they don't if we do such swaps, they don't break the order. Like the order is still good. Then we can like mentally apply bubble sort to our like take good order, then apply bubble sort according to our rule, and since all the transitions we do are fine and we will get to sorted order, then sorted order is fine. So this idea is called exchange argument, like because we trying to change the order by some small steps. So to prove it, we say that okay, there is some prefix of our okay. Once again, what is the idea? We have some greedy. We are trying to prove that this greedy is correct. We say, okay, if there is no right order, then fine. Our greedy will find some order. We will check it is bad, and our answer is correct because answer is no, and we will check and say no. The only way we can do bad if there is some right order, but our greedy finds bad order. So we say, okay, suppose there is some right order. Let's take this order and step by step change it, and we will maintain that after every step order is correct, and in the end we will get sorted order. So we can just take sorted order and it will be fine. To do it, we will prove that every step is fine. If we are having good order and do one simple step of exchanging two consecutive elements such that they will become according to this rule, then everything will be fine. Okay, let's try to prove it. We have some prefix and some suffix. They will remain the same, and what we can see, there is some starting rating. Then we go through all these items, and our rating changes according to these b's, and changes are just add b. So obviously there is no changes on the prefix before we do our exchange. The order is exactly the same. Then for these two elements there will be some changes, but next on the suffix everything is the same because we added exactly the same set of these b's. So when we are what we want is exchange these two elements. And if this order was correct, then this order is also correct. For these elements, everything is fine. For these elements, everything is also fine because it was fine here, and for each element, the multiset of all before them is exactly the same. So we have to look at this. So let's say that rating before this line was x. So what do we know? We know that x is at least a2. This is, I don't know. Okay, x plus b2 is at least a3. And we also know that x plus b2 plus b3 is non-negative, but it's not really important, I think. like, why do we know all that? Because we know that this order was correct. For this order, the rating before this part is also x. But now we want this. And we want this. Okay. We know this. This we know. And this we want to prove. This inequality follows from this one, because b2 is a non-positive value. So we know that if we add something non-positive to x, it will remain like not anything, but if we add b2 which is non-positive to x, it will be none less than a3. So it follows that x is no less than a3 like before adding. And this thing, I say that it also follows from this one. Why is that? Because like now we will use that the swap we want to do is according to this. So a3 plus b3 is at least a2 plus b2. Obviously, if we allow any swap, so then we can get any permutation, and well, it would be stupid so that any order works. But we are allowing only good swaps, so that this will become according to our greedy. And if this is true, well, it is easy to see that from this we know that x is at least a3 minus b2. And from this we know that a3 minus b2 is at least a2 minus b3. Like this is greater than, this is 6. This is greater than a2 minus b3. Well, it is easy to see that this and this is the same. We can move b3 here and b2 here, and this inequality is the same as this one. So from this inequality and this inequality, we get that x is at least a2 minus b3, which is the same as x plus b3 is at least a2. So if we had correct order and we did swap according to our greedy, then our new order is still correct. That means that if we just do sorting according to our greedy, everything will be good. If there exists a correct order, we will find one. So, well, there are some things about what should we do with equal values, but well, it is easy to see that if we had equality here, then everything is fine too. So every greedy order is correct. So let's return to our problem. We have many time left. Oh, cool, it's wrong answer. Let's return to it after we solve problem F. Um, so in F1 we should just check if everything is fine, and we say that okay, we know the correct order. Let's just check if we can do all the operation in this order, and we have to complete all the projects. Well, okay, let's do this. For problem F2, well, we can also choose subset of projects we will complete, but we can see that our order is always correct. Like we can at first what I have said before is let's fix the set of projects we will complete, and then we will show that it is good to sort them according to this order. But now we can do it in reverse. Let's sort in this order, and then for any subset we choose, the sorting is the same. It doesn't depend on anything, like only on these numbers. So let's sort all the bad projects beforehand, and now we will choose what projects we want to complete. And we can do this using DP, which looks like knapsack DP. We will go through these projects one by one from left to right in the order we know, like our greedy order, sorted by A plus B. And for each project, we will decide, do we want to complete it or no? What do we have to know for, like, let's say that we decided everything for some prefix, what should we know? Well, I say that we only have to know what is our current rating and like how many projects we did complete, but we want to maximize it, so it will not be in state of our DP, it will be the value we store in DP. So the state of DP is the prefix of projects we already decided and our current rating. So let's write this. Always write default constructors. It is good for health. We can redefine operator less than, so that we can sort by our greedy, and it looks like this. So it is strict operator less, so here we have strictly greater. So let's remember the whole solution. there will be two phases. In first phase, we just greedily try to complete as many good projects as possible. Well, okay, I don't need this. Let's do it in the most stupid way. So okay, X is our current rating, and is the number of projects we don't need. Well, okay, we do. We do need it for problem of 1. Okay. So if it is greater than 0, well, equal to 0, we can put in any part, it doesn't matter. Solve will return the maximum number of projects you can complete. Okay, in the first phase, we greedily trying to complete any good project we can. If we can complete it, then say, okay, we do complete it. And we should remove it. We should remove it. To do it, we will swap it with the last, which is pos.back, and do pop-back. There is built-in function to remove element from vector, but I don't know it because it is never useful. Like, you always can, well, not always. Okay, maybe there are some uses, but okay, if you have to maintain the order, you can do it by hands, but if you just have vector of some like set of items, you you don't need to maintain them and in order, and you have to remove some items. You can always like swap the element you want to remove with the last one and then do pop back. It works in constant time, while erase, or I don't know how it called, works in linear time, because, well, obviously you should like move all the elements which are on the right from erased one. I did while not found here, because like it is not necessary actually. But let's just do it step by step. So if we found an element, we will do break here, and if not found here, then we finished the first phase. Okay. That shouldn't happen, but Okay, so now we in the second phase. We are dealing with bad projects. We should sort them using our greedy comparator. We we have redefined operator less than, so we can just use built-in sort. So they are sorted in correct order now. We should fill our DP with like bad values. -1 will mean that we can't go to the state. The only state we can go from the beginning is this one, and we can like we have completed 0 projects here, and now we do knapsack DP. If the state is unreachable, then we don't go from it. We can always skip the next project. Or we can take it, but only if we have enough rating to complete it, and after completion our rating will be non-negative. If all of this is true, then we can complete it. Our rating will become this. And we have completed 1 more project, so it's +1. Okay, cool. Well, I do know that at least one of these DPs is not -1 because I always can skip all the bad projects. So 0 here is fine, and I should turn this plus max. And I guess it is better to do this. Okay, cool. So in all the samples, answer is yes. Okay. Since I wrote F2, I will submit it. Why not? Now we can return to G2. Now it is good to wait for verdict for F2 and submit F1 only if F2 is accepted. There was some okay. Cool. So I get 1 cancel test 5. Cool. Oh, I forgot to plus minus here. these two force should be the same, except that we're going from left to right here, and here plus plus everywhere, and we're going from right to left here, and here minus minus everywhere. Okay, cool. I guess that was really wrong. Okay. I guess we can not get a verdict for f2 in time. So okay, let's at least do the coding. So to get the solution for f1, we should check if solve returned n. Okay, so I guess we can wait. Not that long of a queue. Should be fine. So let's test f1. Okay. So am I in top 1000? Whoa! Oh, it's trusted participants. Cool, cool, cool. So I even can be in top 100, maybe. Not sure. Oh, it's running. Cool stuff. Okay, I guess it is safe to submit F1. So, yeah, as I said, E is much easier than even D1 which is, well, yeah, the greedy is not that easy. Well, if f2 is accepted, I guess f1 should be accepted too, if I didn't mistake these 4 lines. So I guess that's all. I hope that was helpful for someone. Thanks for watching. See you in the next screencasts. Bye.